Okay, so thanks for joining today. So this is the sixth session in our series for drinking water. And so today we're going to be going over source water characteristics. Okay, and I did the second session, I think it was, in this series. So it's nice to see you all again and nice to be part of this another time. But my name's Tucker Colvin, and I'm a research scientist with the Southwest Environmental Finance Center. And I'm actually based in Billings, Montana. And so I'm based up here, and I'll be using a few examples from my work up in Montana throughout our training today. And I'm a certified water operator, so that's my background. So let me know if you have any questions about anything. Um, and as you go through the training today too, please put any questions you have in the chat. Um, Matt, my colleague Matt Ziegler, is also on today, and he will be monitoring the chat. And so maybe he'll answer the question in the chat or he'll read it out loud so we can answer it as a group. So thank you, Matt. Okay, and the Southwest Environmental Finance Center is based at the University of New Mexico in the School of Engineering. And this series is funded by the US EPA. So thanks to them for letting us put this on. Okay, and just a quick look at where we are in this series. This is the sixth session out of, I don't even know how many. I think they keep going after this. But today we're going to be talking about source water characteristics, and I'm going to more talk about water itself and the different places we take water from in the environment, whether it's surface water or groundwater. And then next week I'll talk about how the facilities that are used to for intakes, whether it's wells or whether it's in different various intake structures for surface water. So today I'm just going to talk about source water itself and different characteristics of the different places we find water and utilize that water. Okay, so before I talk too much about different places where we're going to find water, like surface water and groundwater, I just want to talk about water characteristics in general. And so we can think about these in kind of three different ways. So we're going to have our physical water parameters, our chemical water parameters, and our biological water parameters. And there's more than just what I'm talking about today, but what I'm going to talk about, I think, are just the ones that are important for drinking water concepts. So first, I'm going to start with the physical water parameters. And the first one of these that I'm going to go over is temperature. So this is something that everybody's familiar with. We all feel it all the time in our daily life. But what temperature actually is, empirically, how it's measured, is it's a measure of the kinetic energy of particles in a substance. And so what that means is that all of the particles in water, in air, in us, and everything, all these particles are moving around, they're dancing, they're vibrating. And so temperature is just a measurement of how quickly all these little molecules are dancing. And so that kinetic means movement. So that's what this kinetic energy means. It's all about movement and all these particles moving around. So this is important for many reasons, and probably most importantly for drinking water and just for our purposes, is that the warmer water is, the more quickly reactions take place. So in order for chemical reactions or physical reactions to take place, they utilize energy or they give off energy. But the warmer the water is, the more energy that is available, the quicker reactions take place. And of course, we kind of intuitively know this. If you think about like brewing a cup of tea or a pot of coffee, it's a heck of a lot easier to brew a cup of tea using hot water than it is cold water. So if you make some sun tea, you put some tea bags or some loose tea in a jar, put it outside. Um, in its cold water, it's going to take a lot longer to brew than it'll take if you're brewing a cup of tea, like I just did. So I just made this a couple minutes ago, and it's hot and good to go. Already steeped. So this is the same kind of concept when it comes to drinking water treatment. Whether we're adding chlorine or other chemicals, the warmer the water is, the quicker those are going to react. Density is the next physical water parameter we'll talk about. And so what the definition of density is, it's the mass of a substance per volume. And so one thing I think is interesting talking about density and with water is the definition of a gram is based on the density of water. So if you have 1 little cubic centimeter of water, it weighs 1 gram. And so that is the kind of the density of water. But water density, it changes depending on temperature. So water is kind of interesting in a way because it's one of the only substances that is less dense when it freezes. But water also changes in density in the liquid form depending on the temperature. So in this graph over here, that my apologies is kind of small, but hopefully it gets the point across, is you can see in this line going down here. So this is really, really cold temperatures going up to warmer and warmer temperatures. And so as water or as ice, I guess, gets warmer, it hits 0 degrees Celsius, which is the freezing point, and then it melts and then it becomes liquid water. So it becomes a lot more dense liquid versus ice. And so then as it gets warmer and warmer, it gets less and less dense. And so you can actually see right here, though, that water that is right at the freezing point at 0 degrees Celsius is slightly less dense than water that is about 4 degrees Celsius. And so then after about 4 degrees Celsius, then it drops off and gets less and less dense. So it's kind of interesting that water does that. And that makes a difference because as water is flowing in different or is in different like bodies, whether it's a lake or whether it's throughout a treatment process, that different temperature is going to stratify waters or like the profile of water. So in lakes for around me, for example, this may not be the case where all you are. You probably don't get frozen lakes in the winter, but around here we do. And so in the summer, we have our hottest temperature water at the top where it's getting energy from the sun. And then it gets deeper or it gets more dense as the temperature gets cooler as we go down. But then in the winter, it's going to be the opposite. So it's cold air is keeping the water cool, but then it actually has the water that is the warmest at the bottom. But then as the spring happens, that that is going to switch. So during that transition, this water is going to flip. And so it's actually going to mix up all the water in this lake. And that can have a pretty big impact for the water quality in the lake and how we're treating that water because all of a sudden our water chemistry and the physical parameters of the water is going to change. The last physical water parameter that I'll talk about is polarity. And so you've probably seen this diagram before. So this is the water molecule. And so you can see our hydrogen and our oxygen atoms over here. So two hydrogen, one oxygen, H2O. And so in this graphic, you can see this red and this blue. So the red is going to be a net negative charge, and the blue is going to be a positive charge. So you can think of this as like a magnet. And this is important because this makes it so water molecules attach to each other and make these rings. And it also means that water works as a very good solvent. So things are able to dissolve in water typically very easily because of this polarity. And this is important because we're adding all kinds of chemicals to water to treat it in the treatment process. And that polarity is used with chemicals to help it dissolve. Okay, so those are our physical parameters. And now we're going to move on to our chemical parameters. So the first ones I'm going to talk about are pH and alkalinity. And these are used sometimes interchangeably, but they're not the same thing, and I'll talk about why and how they relate to each other. So you've all probably heard pH, but what is that actually measuring? What is pH? We know it's like acid, base, but pH is actually a measurement of hydrogen ions in the water. And so hydrogen ions are actually just protons. And so what we are is we're just measuring the amount of hydrogen ions, and then it's just the negative log of that measurement. And that puts us onto this scale that goes from 0 to 14, with on this side the acids having more hydrogen ions over here. So this is 7 down, And then 7 up to 14 has more of these hydroxide molecules. So that's what we're actually measuring, or is what really the definition of pH is. And of course, we're going to have all kinds of different reactions of how our water interacts with different chemicals based on what is in that water, whether it's more hydrogen ions or more hydroxide ions. And so pure water is going to be a pH of 7, but because most water, unless you specifically purify it through some process, is going to have things dissolved in it. And that is what is going to either make that water more acidic or more basic. Okay, and pH is usually measured with a probe like this. So you can see it's just like a little electronic meter with a probe attached to it. And this is interesting, and I think it's kind of fun to talk about when it comes to surface water, especially, is because pH actually changes daily for surface water because of the process of photosynthesis. So, photosynthesis is the process that like plants and some like bacteria and organisms use to create energy. And so they take in energy from that sun, and then they release carbon dioxide. So during the day, when plants and algae are taking in carbon dioxide for their photosynthesis process, um, they are taking in that carbon dioxide from the water, which when it's dissolved in water is called carbonic acid, and that actually increases the pH. So when the carbon dioxide is an acid, and so it shifts the pH more lower on this side, and then during the nighttime, when that photosynthesis stops, and there's other organisms that are in that water doing respiration, which is the process we do for our metabolism, we release CO2. So we breathe out carbon dioxide, and then that actually decreases the pH. Excuse me, I had these backwards. Increases up here, decreases down there. So during the day, there's increased pH. During the night, there's decreased pH. Excuse me, I was mixing those up, but yeah, so there's decreased carbon dioxide, and that is increasing the pH because that's an acid. Okay, my apologies for mixing that up. Okay, and so how does that relate to alkalinity? So alkalinity is related to pH, but what alkalinity is actually a measurement of is it's the ability of water to resist acidification. So this is measured through titrations. So maybe you did this at some point in a high school or college chemistry class. And so basically, you have the water in this little beaker and you keep adding acid and you see how much acid you add to the water before it gets to a certain pH. And then when you get to a certain pH, there's a indicator in there that will turn it pink or purple or something. And so this is important because the more alkalinity there is in water, it decreases like corrosion, and it's also that alkalinity, the molecules that and the stuff that's dissolved in there, they are important for treatment processes as well. Okay. Okay, moving on to other chemical parameters, and feel free to put any questions in the chat. I know these are concepts that we could spend a whole class on, and we're going through them really quick. So, but I think it's important to have an understanding of what these things are because you do hear about it all the time in drinking water and wastewater. Okay, turbidity is just the measurement of the cloudiness of water. So turbidity, it's really just like a proxy for measuring the cloudiness of water. And it's the unit that you measured in is called nephelometric turbidity units. And this is measured a few different ways. So, in like a surface water situation, like in a lake, you can use one of these Secchi discs. And so it's just basically this black and white disc, and you put it down in the water and you see how far you can see it. And then that gives you an idea of just how much stuff there is, how much sediment there is in that water. Of course, the more stuff there is in the water, the harder it is to see. And then in a wastewater process or if you're out in the field and you have like a handheld turbidimeter, It's done by just having a simple, like either the water flowing through some vessel or putting water in a vial, and then it just measures, it just shines a light through it, and then just measures how much light goes through it, um, and then gives you that reading. Um, and then, so that's how you measure turbidity, and it really is just a proxy for how much stuff is in the water, and it's how much stuff is suspended in the water. And this is related to suspended solids. And so this is just like an actual measurement of how much stuff is actually in the water, where turbidity is more of a proxy for how much stuff is in there. Suspended solids is the actual stuff that is in there. So suspended solids, a lot of times you'll hear this as total suspended solids or TSS. And so that's like kind of when you measure it for water treatment or if you're in the field or something like that. Um, you measure this as total suspended solids. And the way you do this is you put water into a beaker like this or like this apparatus. So it's a like a funnel up here where you put water into a certain quantity of water and then you push it through this 2 micron filter, or I guess use like a vacuum to suck that water through. And then you see how much stuff is left behind. And then you can weigh that and you can see how much suspended solids are are left on that filter, and that's how much was in that water. Okay, and there's suspended solids, and the kind of opposite of that is dissolved solids. So this is also called total dissolved solids or TDS when you're measuring it. And what this is, it's similar to total suspended solids, but it's stuff that's actually dissolved in the water, so incorporated into like the structure, like more of the molecules of that water. And so it's more minerals, metals, salt, organic matter. It could be really whatever. And really, the big difference between total suspended solids and total dissolved solids is really just what makes it through that 2 micron filter versus what doesn't. Um, and so you measure it really, or I guess in concept, it's the same thing as what is in this process, but instead of what is left behind in this funnel and on the filter, it's what goes through into this beaker. But to measure it, you can actually measure it with a conductivity meter, and that's the most typical way to measure it. And so a conductivity meter is just a probe similar to that pH probe. You put it in the water, and it has like electrical. It sees how easily electrical charge goes through that water. Because water itself actually isn't very conductive and has to have stuff dissolved in it in order to conduct electricity. So the more stuff that's in that water, the more that electricity is going to go through the water. And so that's how you measure it. You can also measure it by taking this water that you filtered and then evaporating it and then seeing what's left behind too. I've never done that method, but that would also work. Just a little more effort, but probably more accurate. Okay, another concept that's related but not necessarily the same is hardness. So this is probably something you've all heard. Um, Something that people talk a lot, at least around here, like, oh, this town has really hard water and this town has really soft water and stuff like that. And it's because it's kind of a pain in the butt because hard water, it's what it really is dissolved calcium and manganese salts in that water, but it's a pain because it creates scale on pipes, which can also lead to some corrosion. But it makes it so you need to use a lot of soap to take a shower or do your dishes and stuff. So it's hardness isn't necessarily bad for health, but a lot of places treat for hardness with water softeners and stuff because it's inconvenient to deal with. Okay. And I kind of mentioned this or alluded to this, corrosivity. So corrosivity, what that is technically is the ability of water to dissolve metals. And so here we have just a photo of some pipes, looks like some copper pipe and then some galvanized pipe. That water is corroding that away. So um, corrosivity, it is like a complex chemical reaction of what kind of water does corrode metal. But basically, it's oxidizing it so that water is taking away. is stripping that metal and putting it into the solution of the water. And because it's a complex kind of reaction between all kinds of different chemical aspects and physical aspects of water, it's kind of hard to determine exactly the corrosivity of water, but there are some models that predict it. So like the Reisner index or the Langmuir saturation index. And so these are models that you can put in all these different water parameters and it will predict whether your water is going to be corrosive or not. And they work pretty well. Okay. And then oxidation reduction potential. So this is a chemical parameter of water that really just means the ability of that water or what's dissolved and what's dissolved in that water to give or receive a electron. So this has to do with the oxidation reduction reactions. And so that is just uh, the oxidation is losing electrons, reducing is gaining electrons. And so this is just a measurement of how the ability of water to do that. And this can be positive if it's more oxidizing, or negative if it's more reducing. And this is basically just kind of something you can measure because it gives you a gauge about a water's ability to support biological processes and break down contaminants. Okay, we're getting close to the end of all these water parameters, so don't worry. At least the chemical ones. Okay, the next one we'll talk about is dissolved oxygen. So this is a pretty straightforward concept because it says it right in the title. It's the amount of oxygen that is dissolved in water, and it is oxygen that is available to aquatic organisms. And of course, a lot of aquatic organisms, they need oxygen just like we need oxygen. And so measuring the dissolved oxygen can be an indicator of aquatic health. And you measure dissolved oxygen with one of these probes. Of course, this is similar to that pH probe, or this one is a pH probe, but similar to like the one in the last photo, but this one is more for the field. And there's all kinds of probes on the end of this that measure different things, specific conductivity, temperature, and then, yeah, dissolved organic matter, I guess, dissolved oxygen. So there's a lot of things on this probe. This is the fancy one. The one I use isn't quite this fancy. And then color. So color is another chemical parameter because it's things that are dissolved in the water that are giving it a color. A lot of times this is created by dissolved organic material. If you think about if you put leaves in a bucket and then you put it on the rain, all those, it kind of makes the water all brown and gross. Kind of similar process in like a lake or something that could happen. A lot of times color is also created by algae. So here's a nice green lake that looks very yucky, but it's obviously making it green. Might be hard to remove with treatment. And then also the color can be created by sediment or dissolved solids. If you ever go to places in like the north, very far south latitudes where there's glaciers, a lot of times there's glacial silt, and it makes these lakes a very kind of I don't know, neon-y blue. They're really pretty and really cool looking. And so color isn't necessarily dangerous, but it can be unpleasant if people are drinking their water and they take it out of the tap and it looks kind of green or brown. So don't want that. Woo, okay. So that was all the chemical water parameters went through. And now we're going to talk about the biological water parameters. So this one we're going to go through a little quicker. Okay, so the thing that we're really concerned about in water is pathogens. This is for drinking water. And so for drinking water, we of course don't want to get our customers, our community sick. So we care about what pathogens are in the water. So this can include viruses such as neurovirus, rotavirus, hepatitis A, and others. It can be bacteria. So it can be, I'm probably not going to be able to pronounce all these, but E. coli, uh, well, this bacteria causes dysentery, typhoid, cholera, tuberculosis, and there's more than that too. So of course we want to avoid that in our community. So then there's the biggest organisms, and so viruses are the smallest, then bacteria, then protozoa. Some of the organisms that are classified as protozoa that we're worried about is Giardia lamblia and Cryptosporidium. And then so these are the smallest viruses over here, then bacteria, then protozoa down here on the bottom right. And so, of course, there's plenty other organisms that are living in water that are not harmful for us. And so, I shouldn't say we generally don't care about those, but there's just bacteria everywhere living on our bodies. Most of the time, it's beneficial or neutral to us, usually not a pathogen. And so, pathogens are the one for drinking water that we really care about. But of course, there's other organisms there that are present in water, and sometimes we use them as indicator organisms. So for drinking water systems, you have to take your bacteriological samples monthly, also called the BACTs, if you ever do those. And so you are testing for E. coli, but also you're just testing for total coliforms. And so these are more just used as an indicator to tell you, oh, there's a lot more bacteria in there. There could be things that are causing, could be pathogens, harmful to people's health. And so this total coliform, um, how it's analyzed, it's based on growing those colony forming units. And so um, and that's in a certain amount of water, how many colonies form from the bacteria and the coliforms that are present in that water. Okay, so now we went through those parameters. And so I wanted to go through those first because I think having those or knowledge of what those are, and of course, some of those we're already familiar with, some of them may be new to people. And some of them you're kind of like, what the heck is oxidation reduction potential? So some of them are new concepts that you probably aren't going to utilize a whole lot. But it's important to know what these concepts are as you're talking about surface water, groundwater, because a lot of the characteristics of these, like the advantages and disadvantages, have to do with those parameters that we just went over. Okay, so now I'm going to talk about the different places we find the water. So surface water, a lot of drinking water systems that utilize surface water, and this can be reservoirs or lakes, or it could be streams. And then groundwater. So this is taking water that's underground in an aquifer and sucking it up through a well, which is essentially just a straw in the ground, and then utilizing that for our drinking water systems. And then the last one is abbreviated to GUDI or GUIDISI or all kinds of different acronyms, but basically what it is groundwater under the direct influence of surface water. So I'm going to talk about that a little more later, but essentially what this is, it's a well that is sucking up water that's in close proximity to a stream. So in this picture, you can see a bunch of green vegetation. There's probably a stream right there. And so this well, it's sucking up groundwater, but essentially what it is just taking water from that stream. It's going through a little bit of ground through the earth and then it's getting sucked up right away. So those are our three main categories when we're talking about the sources of drinking water. Okay, so first I'm going to talk about surface water. So with surface water, these are, of course, you're all familiar with lakes and streams, but what we're really utilizing here is the concept of a watershed. So this is an example from the drinking water system that I worked at in Bozeman, Montana, where I used to be an operator. So they have two drinking water sources, this watershed right here, and actually this one just right to the southwest of it. And so because water always flows downhill because of gravity, and this is a pretty mountainous region, so you can delineate all the water that is going to, if it falls onto the earth, it's going to eventually flow because of gravity down to a certain point. So in this yellow area here, which is the same thing as here, just with a different background, this is just the topographic map, so you can see these topo lines, the elevation, and this is just the satellite imagery. So all the water that's going to drop into here, it's going to eventually flow down these creeks to the lowest point right here. And so at this lowest point, where this little blue indicator is, this is where the diversion is to take that water in that stream and bring it into the water plant to treat it and then bring it and then send it out to the community. And so this is kind of the concept of the surface water that flows into this specific point. And this is a stream in this example, but it could be a lake too. So there's a lake down here that is the other source of water for the city of Bozeman. And so this lake is, of course, going to be the same thing. It's going to collect all the water that is that falls on the land that is above that. So it'll flow down into that lake. Okay, so surface water has some advantages. And this is advantages versus groundwater, so versus an aquifer, which we'll talk about more in a minute. But, excuse me. So surface water, it can be less likely to have dissolved contaminants because it's not flowing through the earth and picking up all these minerals as it flows through the ground. There's probably less dissolved contaminants that we need to treat for. And because there's less stuff dissolved in it, that probably means it's softer water. So versus where groundwater could be harder, this water is probably softer, less calcium and magnesium salts. It's also a lot more accessible typically than groundwater. I mean, just right there, there's a lake or there's a creek. If you're in a place where you're lucky enough to have surface water, where sometimes in the deserty areas or in New Mexico, that's not the case. But it can be a lot easier to access versus an aquifer. It's a little more abstract of where it is and how it flows, and you might have to drill some test wells to figure out where it is or how deep it is and stuff like that. And then there's some disadvantages too, just like with anything, there's advantages, disadvantages. Disadvantages is that there's more suspended solids and organics. So there's more stuff, more sediment floating in it. And of course, like there's more living organisms that are contaminating this. In this picture, this is a lake I was at recently. There's of course all these seagulls that are hanging out. So um, seagulls are pooping, there's algae in there, there's all kinds of stuff. And so that means there's a lot more pathogens that we have to filter out. And so because of that, there's potentially more expensive treatment because we have to filter out all those pathogens that are there and all the sediment that may be in that surface water. There's a lot of seasonal variability, especially in places like where I live in Montana, maybe less where you all live. But here, seasonally, it's going to freeze, it's going to melt, and then it gets pretty hot in the summer. And so, of course, that changes the water quality, changes all those parameters like I talked about earlier. And then there's also yearly variability. So, a lot of places in the West and Rocky Mountain region right now are in a drought. And so there's going to maybe a lot more water one year, a lot less water one year, and you just have to deal with that or figure out more other sources. Okay, and then there's differences between lakes and streams as well. So some advantages of lakes versus streams. The water quality is more consistent. It's a larger body of water. It takes a lot more time to change that because it's not flowing. It's more constant. And then thus the pH, the temperature, turbidity, they fluctuate a lot less in a creek. And then the length of the detention time. So that just means that water is in there for quite a while, whereas stream, it's flowing all the time. So that aids in the removal of bacteria and suspended solids. And so basically that's done two ways. The sun constantly hitting that surface water is actually going to kill some of the bacteria that's in there. And then second, because water is going very slowly, it's pretty much not moving at all through a lake, there's a lot of time for all that sediment to filter out or not filter out, fall out of suspension, so kind of settle out. So that can be the advantages of a lake versus a stream. But of course, there's disadvantages as well. So this is the photo I took of the duck pond at the University of New Mexico campus. So nice and yucky on that day. So disadvantages of lakes compared to streams, they can concentrate minerals. So just like I was saying that a lot of that sediment and stuff will settle out in a lake, well, that means all those minerals are going to settle out of the bottom. So if you're taking water from a lake, you probably don't want to do it towards the bottom, you want to do it towards the top. And then affected by turnover. So that's when different seasons with changes in density can flip the lake around, really change water quality. That's that stratification. So different water qualities and temperatures depending on how deep you are on the lake. And then this is the big deal too in the West where there's a drought because all the reservoirs are pretty low right now. So where our intake may have been in the water column used to be lower down. Now it's a lot higher up. So it can change a lot, that stratification. Algal blooms are a bigger concern for lakes. And then algal blooms can also lead to eutrophication, which means when there's no oxygen in the water. So a lot of times this happens when the algae have a big algae bloom, usually due to increased nutrients, increased temperature, and then there's a bunch of algae and then they die. And then as that algae is being decomposed, all these respirating organisms, they suck up all the oxygen that's there, and then there's no more oxygen in the water, so it essentially makes a dead zone. So this is what's happening in like the Gulf of Mexico, for example. And there's not a lot of life going on there, and it becomes pretty low quality water. And as we're talking about lakes and algae, I'm going to talk about taste and odor really quick. So taste and odor in water is caused by two main types of algae principally. So green algae, which creates kind of a grassy, musty smell, and then blue-green algae, which is more of a rotten fish kind of smell. And blue-green algae is what is colloquially known as, but it's not actually an algae. It's technically bacteria, and all this bacteria grouped together to look like algae. And this bacteria called cyanobacteria, it can produce toxins called microcystins. And so sometimes you'll hear about these harmful algal blooms, or HABs is what I've heard them called. And that is because of this blue-green algae. And where I worked in that reservoir, we had an algal bloom, and so we were testing it regularly to make sure that it wasn't producing these microcystins, which is toxic. So of course you don't want to have that in your drinking water system. And this was the test that I was doing to test that. And then these blooms, typically hot and dry weather, and to kind of prevent them, or if you have them, you can kill them with copper sulfate at that dosage. So that can kill that algae. Okay, and so rivers and streams compared to lakes is going to pretty much be the opposite of what we talked about with lakes. I'll go through this pretty quick. Minerals do not accumulate in rivers and streams. There's decreased need for the treatment of dissolved contaminants as things like settle out. Um, and then rivers and streams, they have disadvantages though as well compared to reservoirs, excuse me. More temperature fluctuations, just because it's flowing all the time, quicker changes, more pH fluctuations, flow variability depending on the day, the month, the year, all kinds of different changes that happen pretty regularly. Turbidity can be a big issue. Those fluctuations, rainstorms can flush a bunch of turbidity, a bunch of sediment into the creek, and then that can cause an issue. Yeah, and potential for acute water quality issues. So just uh, here's an example of the system that I worked at. This is the creek right here on the left, and it's about our water intake is, I don't know, a couple hundred yards downstream of here of this truck. And so this truck crashed. We had to close that intake for a while and then come up here and make sure that this truck wasn't leaking all kinds of different fluids into the creek. Here's another situation where this is when we had um, a big storm, and these are the two different sources, these two different watersheds right next to each other. There was a big landslide in one of them, and so it just sent down a ton of mud into the creek. And so this is the turbidity, so the NTU, the measurement of that. And so this was what one stream was on one watershed, 2.2 NTU, and the other one is 5,000. So essentially it was just mud coming down there. So we closed out intake for a while, waited for that mud to go through, and then we opened it up like a few days later. Okay, so that's surface water. And the next thing I'm going to talk about just really quickly is this groundwater under direct influence of surface water, or GWIDC. You'll see it pronounced and abbreviated in all different ways. And so this diagram right here kind of, I think, illustrates this decently well. And so if kind of want to look at this section right here. So here's our well that's pumping up water. And so there's a stream down here. And so this water from the stream is essentially just moving through the ground and then just getting pumped up from the well. So essentially what it is even though it's accessed like groundwater, you really are just sucking up the stream water. And so because of that, it's regulated like surface water. And so sometimes you'll see wells close to streams and they'll be regulated more strictly, and you'll have to go through all the treatment methods for surface water because it was determined by the primacy agency that that well is actually sucking up surface water to an extent. Okay, yeah, and like I said, it's accessed via groundwater, but it's actually the surface water that you're being sucked up. There's more risk of pathogens than there would be in groundwater because it is that surface water. And so you have to have more treatment. Okay, and then groundwater. So this is accessed via a well or spring. And so this is an aquifer. So hopefully you've heard that term before. And so this is a diagram of what an aquifer looks like. So you can think of this kind of as a slice of the earth, like maybe looking down a valley with kind of two hills on each side and then a hill in the middle. So if we look at the components of this, this part labeled 1, this kind of blue-green color here. This is our aquifer. So this is water that has fallen onto the earth and then it goes into the ground and it creates this aquifer. These two parts labeled number 2. So these are impervious strata, also called an aquiclude. So you can think of these as being like a bedrock where water cannot flow through, where the where the aquifer is might be more something like gravel or sand that can hold water. These two parts labeled number 3, this is where our aquifer has infiltration. So rain will fall here, and then because this is a sandy composition, the water will flow through and then it'll become incorporated into that aquifer. And then number 4 is an artesian well. So this is a well where you don't actually have to even pump it. You drill a well and the water just gets pushed up naturally. And that's because there's a layer that is like this impervious strata that the water would normally come up through it, but because it can't, it's under pressure. And so that pressure then pushes it up through the well and you don't even need to pump it. So pretty great if you find a well like that. It reduces your pumping costs. Number 5 is our saturation level. So that's kind of, if you think about that with maybe like the level of the water, if you have a glass of water like I do right here, there's the surface of the level of water right there. So if you poke a hole in the glass down here, water's going to flow out. But if I poke a hole up here, there's no water going to flow out of that. And then our number 6, this is more of a regular well that will require a pump down here to pump up the water through that straw. And then the last thing labeled here is a spring. So it's usually sometimes on like a hillside where that aquifer comes into contact with the atmosphere and then it flows out of that hillside. All right, I'll have a drink of water now that I have this in my hand. Okay, so what are the advantages of groundwater versus surface water? So it's going to be kind of the opposite of the disadvantage we talked about with surface water. So there's going to be less suspended solids. So there's not going to be as much like dirt and sediment in there in that water because it has all gotten filtered out as it goes through the earth. And so there's not going to be really any organisms present. So hopefully there's no microbes and bacteria and stuff living in your well, or not a significant amount at least, that are gonna cause any that aren't going to be harmful because it makes it a lot easier to treat. So because there's going to be not any living organisms, hopefully, there's not going to be that log removal requirement. So that just means a percentage you have to remove a certain percentage of the organisms that are living in there. And I'll talk about more about log removal during the treatment sections coming up. But basically, it just means you don't have to put as much effort into removing those organisms. And then, of course, it means there's less expensive treatment because you don't have to remove them. There's less variability seasonally as well as yearly because it's pretty much a big reservoir of water and underground, so it's protected from from more immediate changes. And sometimes aquifers have been there for thousands of years, so they're pretty resistant to change and pretty dependable. Okay, so what are some of the disadvantages of groundwater versus surface water? They can be more likely to have dissolved contaminants because they are flowing through all this earth, all this rock and everything all the time. They can incorporate those and have all that minerals dissolved in that water. So thus it can be harder water, so it can have that calcium and magnesium salts in it, more likely to than surface water. And it can be less accessible because you need to drill for it. It can be expensive. And then there's long-term contamination risks. So if an aquifer gets polluted, it may be polluted essentially forever because it's not like a stream where water is flowing. The water is just there, and it's a lot harder to remediate that pollution. And so here's just a diagram of what a kind of an aquifer looks like with a well going through it. And so in this case, you can see there's two different layers that contain water. So there's this layer up here, and then there's a layer down here. So and then there's some clay that is impeding water movement from these two. So if you're using this water down here, it's going to be much more resistant to contamination than this water up here because it's a lot closer to the soil. So a lot of times you want to use deeper water um, and then less likely for contamination, but sometimes it'll have more stuff dissolved in it if it's deeper. So there's always pros and cons of everything. And so that leads me to source water protection. So whether you're using groundwater or surface water, you want to protect that source from pollution and contamination. And so why do you want to do this? Of course, you want to protect public health. That's what we're doing with providing safe drinking water to communities. We want to promote public health and reduce the amount of contaminants and anything that could be harmful sent to our community. It also decreases treatment costs. So if you're using some kind of source that is really low quality water, sure, you might still be able to use it, but it's going to be really expensive to treat that and to get it to a point where it's safe enough to deliver to the community. And so thinking about pollution that can contaminate our water sources, there's three main types that I'm going to go over. So the first one is going to be point source pollution. And this is kind of what we think about. It is when contaminants are discharged directly into a water body. So you can think of it like pollution coming out of a pipe. Maybe it's from some industrial source. Maybe it's coming from a wastewater treatment plant. But basically, can be it can be kind of determined that it comes out of this specific spot for this specific reason. Non-point solution point excuse me, non-point source pollution, that's contaminants that enter the water bodies because of runoff from places like urban areas or agricultural areas or golf courses. There's all these things all kind of pollutants that are in our urban and our rural environments that are harmful for water bodies, whether it's fertilizer or like engine oil from cities or all kinds of stuff. And so when precipitation events happen, they wash off all of the stuff that's on the surface water into our water bodies, and that's called non-point source pollution. And then lastly, air deposition. So this is aerosolized contaminants. So things that are in the air that are put there for various reasons. Sometimes things like this, in this picture over here. So there's all this smoke. All that smoke is something, and it's going to fall back onto the earth somewhere. And so sometimes it can deposit into water bodies, and we of course don't want that. Okay, and then watershed protection. So how do we protect these areas from different sources of pollution? So this is the example back in Bozeman where I used to work. So we wanted to protect this watershed from sources of pollution. So one of the big things that we noticed in the creek is that there was a lot of E. coli in the stream. So want to figure out where that E. coli is coming from. And so actually somebody at the local university did a study to see what was the source of that E. coli. So we were thinking maybe it's cows or maybe it's wildlife like beavers, but it turns out it was mostly dogs, dog poop. So the city had put in a campaign with all these signs to clean up dog poop and all these bags so people could pick up their dog poop and stuff. Um, so it wasn't contaminating our water anymore. Also, they didn't want people driving up this road because it would decrease the amount of traffic and amount of people in general to decrease the amount of potential contamination to put up a gate. And then wildfire, it's a big thing I guess pretty much everywhere now, especially around here in the West, in the Rocky Mountain region. So they're doing a bunch of harvesting and clearing of trees with the sole purpose of just decreasing the risk of wildfire, because that, of course, has a huge impact on a watershed. Um, in this situation, it was pretty simple because the watershed is just in the mountains right outside of town. But right now, I live in a different town. I live in Billings. And so we get our water straight from the Yellowstone River. And so the Yellowstone River flows through all kinds of communities before it gets to Billings. And so it's a much, much bigger watershed. It's a big portion of the state of Montana. So, of course, it's a lot harder to control um, what other people upstream are doing, what other towns upstream are doing. But that's really why we trust and hope our agencies that are enforcing discharge permits and things like septic tanks are doing a good job because we want to have clean water downstream so we can have minimal treatment requirements for that as well. And then if we think about groundwater, it's going to be the same concept, same ideas, but it's just going to be a little bit different how we kind of delineate that area, how we determine what is the area that our water is coming from that we want to protect. So here's just a little diagram of a well going down into an aquifer, and then there's all these potential sources of contamination, or also called PSOCs. Maybe you might hear that term on occasion. Potential sources of contamination. So there are things like fuel tanks, all kind of different kind of tanks, a sewer line, a septic tank, drain field for a septic system. So all of these can create contamination for your well for that aquifer. This is just what some maybe corroding underground storage tanks would look like. And then just some examples of where I live. This is in Billings. This is a toxic plume of contaminants, some chemical contaminant from dry cleaners. That a bunch of historic dry cleaners and these red dots were just dumping their dry cleaning chemicals down in the alley, and now it's created a big toxic plume underneath downtown in a big part of the city. Of course, that's a big concern for people who live around it, of course, and so good thing we get our water from the river instead. And then this is an example in Albuquerque where I used to live and where colleagues and Matt lives. This is a leak. There was a leak in a storage tank for jet fuels at the Air Force Base. And this was leaking into the aquifer for 30 or something years or so, and it created a big toxic plume of jet fuel in the water. So of course, don't want to suck up water and utilize that for drinking water. So, and these are pretty big tasks to remediate. And so when you're thinking about how to protect your source, what are the steps to do this? And this is kind of the phases that you go through. So first phase is delineate the source water protection area. So what is the area that our water is coming from that we need to protect? So figure out what that is. And then inventory the known potential sources of contamination. So those are things like storage tanks. They're things like dog walkers that don't pick up their dog poop. There are all kinds of things depending on what your situation is. And then you determine that susceptibility. So every potential source of contamination, you want to analyze how likely is it that that's going to contaminate our source, and if it does contaminate our source, how serious is that going to be? You want to engage the public to learn more from the public and to communicate these threats with the public. And then you want to protect your source. So you develop an action plan on how you identify and prioritize these specific kind of actions you want to take of how you protect these. Do you need to remove some of these leaking storage tanks, or what is your action plan for that? And then you protect your sources, and then you evaluate, and you kind of update this constantly. This is not something you is one and done. You want to constantly go through this process to think about what are the sources, how do I keep protecting my water source from these adapting threats of contamination. And so just to look at one of those, this is one that we did for the city of Espanola, New Mexico. So you can just see a bunch of different things here. Domestic water wells. So these are just wells in people's backyard. Could be a source of contamination. You don't know. Maybe they're dumping their paint cans down there or their motor oil. Who knows? And so you don't want them to do that. So that's a potential source of contamination. And then there's these bigger things. This is like a big plume, I think also from a dry cleaner, maybe from the railroad. I don't remember exactly what this one is from. But of course, you don't want to suck up water from there. And there used to be a domestic or a well for the water system in there that they had to retire, of course, because don't want to suck up that contamination. And then thinking about these wells, so here's 3 wells that the city's using for their drinking water. So depending on the production and how deep these wells are, you want to protect to a certain distance away from these. And so you can map out um, what all of these threats are. So these are point of divergence. So these are probably wells that are here. Could be a contaminant source. And then there's these petroleum tanks. So you want to make sure that these are not leaking and not contaminating our source. And then you can do this for the whole community, and then you can kind of get a strategy for what do we need to focus on? Do we need to retire any wells or not use them because there's too much contamination, like this one down here that we talked about it earlier in this big by this big plume. And then for each of these sources, you can kind of analyze them for specific threats. So whether they're naturally occurring, so like this well, there's a potential arsenic contamination. Of course, that's naturally occurring in this area. And so what is the risk to that for that well? And for this one, quite high. So the idea is that you can go through this with all your different sources and kind of gauge the likelihood of contamination and how to best protect those. All right, and so kind of going through this whole process and thinking about these, there's all these kind of requirements for environmental requirements, but they're a lot of times is to protect our source water quality, and then that impacts our water treatment and it impacts public health, and then that has to do with our source water protection. So it really is a whole cycle of thinking about these things. What's our water like? What do we need to protect our water, and how does that relate to our community and public health? So that's it. So thank you. And we have just a few more minutes. So happy to take some questions. It's just about an hour. Let me see. Any questions in the chat, Matt?
We haven't had any yet, Tucker. But if anybody wants to put one in the chat, let us know.